you're a physicist, astronomer, mathematician, or even an engineer like myself, or someone who watched the Netflix series, you probably have already heard of the three-body problem. The three-body problem is a famous physics problem to which no one has yet found an analytical solution. In other words, there is no closed formula that we can use to correctly predict the motion of the bodies. It is still numerically possible to obtain a solution, but you do have to iterate over a number of equations to get it. And this is where things get interesting. This type of problem is inherently chaotic. This means that the initial conditions have a huge impact on the outcome of the motion and the solution of the problem. So even if you have the best computer to compute all those iterations, if you miss a tiny bit on the initial conditions correctly, the solution goes horribly wrong. The problem in itself is very simple. You are given three bodies that attract each other as ruled by Newton's gravity equation. The question is, how do you precisely predict the motion? In other words, the position and the velocity of all the bodies at any time? We don't know how to answer that analytically. Alright, let's say the numerical solution is totally fine. Still, how would you software engineer your way to build your own three-body simulator, or even an n-body simulator? Yes, it's totally possible to scale your three-body problem to a n-body problem very easily. And this is exactly what you will be learning in this video today. In today's video, I will show you how to approach this kind of problem by creating your own simulator with a bit of software engineering thinking. So this means that I will bring you some practical concepts, for example, data structures, factories, UML design, interface design, and others, so that you are completely capable of writing your own n-body problem simulator yourself. Of course, this is not the only way to approach this problem. There could be easy ways to approach this problem, but I think this is a good opportunity to learn about some software concepts that we apply in practice. My name is Marcos, and this is Practical Software. Alright, so first things first, let's establish what we want. We want a n-body simulator. We want to be able to add bodies or remove bodies from a system. We want the system to be able to compute those interactions between the bodies. This is the responsibility of the system. So add or remove bodies. System is responsible for calculating the forces of the bodies among themselves. And finally, we want the system to be visually represented. And I think this is enough. By the way, this setup, this VS Code that you see here on the right side, this is a container, a dev container. If you want to know more, there's a video about it. This is a dev container that contains a lot of things to work and develop. This is what it is for. So it's a container that has CMake. I also have a video on it. It has UML renderer. So I could just write something like this. It's gonna render whatever I just wrote as a UML diagram, a class diagram. So we can put into words or actually put into diagrams what we describe as a system. And there is a Clang format. There is so much in this dev container. And yeah, I'll make sure everything that is really important for this video is covered. Now let's get into the components of the system. So naturally, we can describe a body and a system. And I think we know the relationship between the two. So the system can contain one or more bodies. And this is how we would describe in UML. So we have a body. It has a certain multiplicity relationship with the system, and the system is 1, and this is a small hack to get some spaces for free, and this is what we have now. So my system can contain one or more body. Notice the relationship kind here, it is an aggregate, meaning that the body itself is a thing, it's a standalone thing. It doesn't depend on the system, it can live by its own. And this is how we would inject the bodies into the system. So we can just add them as we want. So they could have been compositions, meaning that they wouldn't live without a system, but I think this is a better way. This is more decoupled. This is a nicer, in my opinion, to connect those two entities. All right, so let's now think about the components, or should I say the properties of the body. Those are private properties. They don't matter for externally, whoever uses the body externally. And those are the mass. We have volume. Maybe it's important for rendering purposes. We have a color. It's not really important also for the body itself or the system. Maybe it's useful for the third requirement, which is a visual representation of the body. I think color is a good thing. And naturally, we have a position and a velocity. And okay, so those are all private properties. How am I supposed to update something about those properties? And how do I know which one of them are actually something that I want to update? Do I want to update the color or the mass or the volume? Maybe not, but the position and velocity, those are important things to be updated. So I think it's important that we add an update method that takes in, if we remember Newton's law, we can exert a force over a body, and this resultant force will yield a acceleration. So I think it's a good thing that we add here. So acceleration, and let's say just a rate. So if you see this right now, maybe this is enough to realize something about the system. Now, looking into our third requirement, visually representable in real time, let's think about how we can approach it. I'm thinking about creating a class called iSystemPublisher. This is clearly a interface because I can already think of multiple implementation of this. Maybe we want to publish the system in the console or over the network or whatever. So this is already an interface, clearly an interface. I'm gonna state that the implementation should inherit this class and implement this method. I'm gonna call it publish, and this is gonna take iSystem as an input. For completeness purposes, I'm already, I'm gonna make a concrete class of the system and call it Newton system. Yes. So Newton system implements iSystem. Now, very important remark here is that my interface, system publisher interface, it does not take a Newton system as an input. It takes iSystem as an input because I want my system publisher not to care about system implementations. So it should depend on interface. And this is a solid principle. I may talk about this in another video. This is a very important principle that the interfaces depend on interfaces and not, because this makes clear that the implementations don't matter. What matters is the relationship between the objects. And this we state this clearly as the iSystem publisher uses any kind of system. Whoever implements the type of system doesn't matter. It depends on its interface or its parent class. Yeah, let's think about some concrete classes for this iSystem publisher. So of course we can think of the console publisher. It's something that just writes down all the bodies. We can think about the null publisher. Sometimes it's useful to create objects that doesn't do much. Let's say highly performant. So imagine in my real time I want to pick the publisher that doesn't take much resources, and I can just pick the null publisher that doesn't do anything. It's just an operation, no op. And finally, the most fun one, which is I'm gonna call it gRPC publisher. It is the third implementation of this interface that reads the system bodies and their positions or velocities, and it will publish all the messages, all the body positions over the network to another system that will interpret it correctly. In this context, it is a OpenGL server that is listening for RPC calls to draw particular entities on your screen. Now, talking about design choices, I think that this gRPC publisher is particularly interesting because I'm about to create a 3-body or any body simulator, but I don't want to couple this problem or this algorithm simulator with a full-fledged rendering engine. I don't want to couple those two. I want them to be really separate, because then the whole simulator can be its own thing. It doesn't have this huge dependency, which is a whole, graphics library, just to be able to see things. So the seeing is not very important. Why should it be a dependency on my system? So what I did, and I think was a good design choice, is the publishing of the system is but a very tiny implementation detail of a interface. So it's a small thing. It shouldn't matter much. It doesn't bring the graphics library as a dependency to my system. What is happening here is that this publisher is gonna send to somewhere else, and then somewhere else we take care of all these entities and render them properly. And this decouples the things. It's arguably not very performant because I may be able to share millions of bodies over the network. Maybe it's not very good to do that, but still it's decoupled, and maybe it's good enough for a long list of use cases. Okay, we have maybe seen enough of UML design. I think we are ready to see some actual code, to see more or less how it's working under the hood. So now I'm going to explain more about the development environment. So this whole thing, this whole system simulator was built inside a dev container. Now the dev container is a very simple one. What I did was I just installed, it's a Ubuntu OS based container, and it contains pre-installed a lot of dependencies already. So Git, CMake, compilers, algebra library, this plant UML, which is rendering all those UML designs, is part of the container actually. Something to parse a JSON file. We're gonna see more about this later on. Clang format and clang tidy and clang d, and mocking library. And this is just the gRPC compilation phase. So gRPC is also part of the container. And what I like a lot about this dev container thing is that this was all I had to do. So my whole container is really a standalone development machine. I can just clone this whatever machine and just start coding. And I built like this. So I didn't do anything. I just cloned this and this just built. The dev container JSON has some useful extensions already, also part of the repository. So if you clone this, you're gonna get what you see here. It has a mounting, so this build folder here is mounted as a volume, so it's cached. It doesn't need to be saved in my machine. It doesn't need to be persistent, but it need to be a volume that it's to be mounted when we load this container. And this is a reference to the Docker file. So this is how I set up this. Now let's have a look at the CMake. So the CMake has, the dependencies are explicited at here. These are the source files. I'm gonna go into them right now in a few moments. I'm gonna explicit my dependencies, my libraries, my apps. So I made a app for the solar system and one for any body simulator, and this is just a formatting CMake, let's say a target, so I can just format my code every time I build it, which is really nice. So starting from the main class, it's not really a main class, it's an important class, it's the body class. Let me make this bigger. So the body class, as we saw in the diagram, it has those properties, so velocity, position, mass, volume, color. This is very important update method. Of course, it has a constructor also to take in all of these and just create a body out of those descriptions or arguments. Now about the update method is really simple. So all we have to do is feed it from a force, let's say force, so we compute a acceleration externally, and then we use this acceleration to update this current position at any time. And we have to give it a delta t, so all accelerations, all those motion descriptions usually take the difference of time so we know how much exactly it moves. So this is important. This is an API, let's say API to the body. Whenever I want to update the body, I just call this function and give it an argument as an acceleration. Now the system class, like we saw in the previous diagram, it has a single function, step. Actually, it's what we want to see is the iBody system. So in the diagram, it was written as iSystem, but this is iBody system. It works anyway. And this we see very basic data structures that I thought using was nice, and already some, let's say, implemented methods, useful methods for the class. So those methods, they are really stupid. It's not important for inherited classes to take over them. So the interface class or the abstract class already does take care of this. So the body, add body and remove body, this is part of the interface. So whenever whoever inherits this is already owning a little bit of functionality, because this is really simple. It doesn't need much, thinking and details to be, abstracted from somewhere else. And of course we have a getter for the bodies. And this getter is very important because we have a system publisher, and the system publisher must, process all the bodies. So it forwards all the information somewhere else. This is the getter. And finally, the data structure that I chose to store all the bodies was an unordered map or a hash map. So I think it's really important because it is a key value table. So my bodies are in a way unique. So if I can give them a name to the bodies, let's say I wanted to simulate the solar system, so I can add the Earth as a name, or the Sun, Jupiter, Mars. So they all, in the system, they have a name. So they are not properties of the body. So this is important. They are properties of the system. The system is responsible for tagging them or labeling them and using this labeling logic in its own implementation. Also, very important is that the body, I decided to use a share pointer to share ownership of the body. So the system, like we saw before, the system will not keep the bodies inside it. It's just gonna have it passed somewhere else. And the share point is a very nice functionality that allows us, not to care too much about the memory leak and delete and ownership. So I can create all those bodies somewhere else and just pass their pointers to the system. So they are two separate things, but they are related with the share pointer. And also using share pointers like this, it also states that they are not unique pointers in a sense that the system does not own the bodies. The system simply uses them, but it doesn't own them. I also took the liberty to explicitly use a gravity constant, so we want different gravity constants. If we lived in a different universe, maybe this was a different number. It doesn't matter much, but it's part of the system because it's part of the formula that we compute. And here we see that this very important step, which is just this iteration over, so we compute all the forces of all the bodies, that they search on each other, and the step is the implementation that will take care of this. And this is, as stated by the interface, this is to be implemented. And I have an example of the system. So this is iBody system, and this is the body system. This is one implementation. See how simple it is to simulate a n-body system. This is all you have to do. So on the step function, we go through all the bodies in the system that were added to the system. So we process them all. I added a special logic to ignore some of those bodies if they are static. And if you look at the interface, you might have noticed this. So if I add a body and I tell this is a static body, it is not part of it. It is not a body that suffers actions from others, influences from other forces. It just distributes its force among others. So back to the Newton body system simulator, we ignore those that were stated static. We simply, all we have to do is add up all the accelerations that were coming from other bodies into a body, one at a time. So there's another loop here, a for loop. The process was for all the bodies. Of course, if all the bodies, because I'm going through two loops, right? This is the first one, this is the second one. If they are referring to the same thing, don't do anything, just continue, see the next one, because let's say the Earth cannot exert force on its own. So I have to, exclude this law. And if it's any other body other than yourself, then we want to compute the force from Newton. And the force is really simple. So if you see here, the force that a body exerts on one another is computed by this formula. It's exactly as it's written here. So the distance vector, this is given by r. This is just a difference in position. So body A minus body B, there's a vector between the two. This distance vector is just the position difference. And I compute the actual distance as a norm, right? So distance vector is like an arrow pointing to each other, and the norm is the actual distance. The direction is just this normalized vector, so it's this distance vector, but with norm 1. It's just a direction. It doesn't have any, let's say, scale to it. And the acceleration is simply the gravity constant. So right here, g times the other body's mass divided by this distance squared. Of course, don't look at the m1, so we don't look at our own mass, we look at the other's mass, because if we want to see the acceleration equals, or should I say force equals mass times acceleration. So this mass is, cancelled out if I replace by this formula. So all we have is the force exerted by the other bodies on ourselves. Okay, too much physics. It's not important, trust me, it works. And finally, once we have all the accelerations added up from all the bodies, notice this is a 3-dimensional vector, we call the update for the body right here. And this is actually the whole simulator, this loop. This is a O of n squared complexity function. Now, another thing I wanted to show you in this repository is factories. So factories are, let's look at their header files first. Factories are a mechanism that allows you to abstract away a little bit on the creation of objects. Maybe the creation of objects with all its details of creation, which are important for the constructor, maybe they are not important for whoever calls and construct the methods. So for example, I have a body. The body takes quite a number of input arguments to its constructor. Maybe I want to create a factory that I tell create a body, let's say, or even create a random body. I could have done that. Or create a number of random bodies, also possible. So the factory is useful when we're gonna do such a thing. I don't want my, let's say, my application code to care much about all those arguments. So I can create factories, and factories usually are functions. Sometimes they are classes. And this was also important for instantiating those publishers. So if you look at the diagram again, we see there are 3 types of publishers, and maybe my application code also shouldn't care about details of creating, well, some of them. Maybe, for example, the gRPC publisher, it takes an address. I don't care about the address. Maybe it's the same one. So I create factories for those. So let's have a look at them. There are 2 factories at this file. So create null body and create console body. And their implementations lie in the source folder. So this is really straightforward. So this particular classes publishers are not very complicated, but I think it was still useful to prove the concept. Very important thing, especially for C++, factories usually return unique pointers. The reason being that usually whoever uses the factory wants to own the object. It was just conceived, and then the class that uses the function wants to use this object as its own thing. Maybe this user code that calls this create console body system publisher, maybe it wants to convert this unique pointer to a share pointer. It can, because it owns this. It can do whatever it wants with this object, and the factory is very clear. If we quickly look into the implementations of those factories, we just saw it. But actual publishers, they are really straightforward. So the null body publisher doesn't do anything. It's just this console override. But this one is important, but also very simple. So the console body, as stated by the 3rd requirement, we're gonna see a visual representation of the system. I think this is 1. So the console publisher publishes the whole system note again that we take the interface and we call the interface method implementation on the get bodies like this, and we process all the bodies, we get a position, and then we just print out the whole body, or should I say the whole system. So really straightforward. It's just process all the loops, process in the loop all the bodies, and then print out all their positions. It works. And finally, the gRPC publisher, it is also a factory, a very simple one. I've just abstracted away its internal IP, so the application doesn't need to care. Since I will be likely using this application from within the Docker, this won't change, I suppose. But the persistent drawing is a mechanism to, tell this other engine that is listening for this calls. Whatever I draw, keep it in the scene. Don't remove it. Don't update it. So there is a mechanism to do that as well. And the class is also very straightforward. This is plain gRPC client code, so nothing secret here. I have a proto that allows me to interact with this OpenGL gRPC server that I made, and these are the calls. So we can add points, we can add point clouds, we can stream point clouds. We can stream named points, so those are points that have names. It's a nice name to give them, actually. And there is a call that I can tell the renderer just remove everything from the scene. All right, the publisher implementation is also very simple. It is just filling in proto data and streaming them from the client to the server. I think what is important to notice here is that I have a stream connection to the server. So what I do is I have a class that holds this object, stream writer, and whenever my app calls publish, the connection is already opened. I simply push data to this network socket, which is a really nice thing about gRPC. You can keep the connection open and stream data, and this is faster than opening a connection, putting a point here, for example, and then close the connection and do it all over. So I think this is a fast way to use this OpenGL server. We can just stream data to it, and it's gonna really quickly fill in my scene, my render scene. And now, one of the coolest thing I did for this project was to create a factory. If you look at the factories again, there is a body system factory that takes a file as an interface. So there is a create body system factory method that spawns a body system, complete body system based on a file description. What it does is, not gonna go too much into details, but this is where I use the JSON CPP library to process a JSON file. And this JSON file contains whatever we want to be part of this body system. Yeah, it's better that I show you. This is how it looks like. I can specify the gravity constant, I can specify the body as an array, and I can put as many bodies as I want here. And I can give the bodies their constructor arguments very easily. And it works in real time, so I can change this file whenever I want to rerun the simulation with new initial conditions. So yeah, I can give the mass, the volume, and the color, and I can give it a name. And I can have different configurations. So for example, this one is, I think this one is only two, no, it's a 3-body system, so red, green, blue. This one is a 5 body system, but I can, just add more here, and it's just gonna, put everything in the scene and simulate the interactions of the forces. So I think I'm really proud of this particular factory method here. I look for the the fields in the JSON file and just fill them accordingly with a very fancy initializer, uniform initializer list. All right, so maybe this is enough code. Let's see what this system can do. Okay, first things first. I have this is the OpenGL application. Not too much into details here, but this library that I made, it is it is an OpenGL application that allows server calls to fill your scene for you. So all I have to do is just call this, and we should see a black screen, and I don't have to do anything with the other app anymore. Just leave it open. And let's now start from within the Docker, so keep that in mind. Let's start our end body system. So as I have already built it, by the way, just notice how the formatter works. Yeah, every time I build it, it formats. This is really nice. So it's building again. Yeah, it's ready. I'm gonna call it from the terminal. So end body system, what I'm calling is, according to CMake lists, what I'm calling is this executable end body sim. I've placed it in this app folder, and it's really simple. All it does, it has a default JSON file to look for, but I can give it a different argument. And it uses that very nice factory method that I created. Notice how this interface is really easy. So the way I use those interfaces and define those interfaces and factories, it's really easy to create your own simulator like this. So I have a console publisher. I'm gonna uncomment this for now, so to see it. And notice that this is, yeah, it is just the same interface from the other publisher. And this is the persistent publisher. So here's where I feed this argument, and this is the false one. So this gRPC publisher, it publishes the real-time updates of the body. So this is where they move, and their position actually changes over time. This static publisher or persistent publisher is responsible for publishing the current positions, but in a different size. It's a smaller size, and it's in the same positions of the body, but it's just a smaller size, and it's like a snapshot of the positions of the bodies of the same system. So notice I have a single system, and I publish it in different ways. Let's just call this thing. So in body system, it expects an argument, and I'm gonna use the argument, the basic system JSON. This is the console publisher working, and this is the end body system working. This is really cool. Let me make this bigger. So here we can see, yeah, how chaotic this thing is. So 3 bodies are interacting with each other. 2 of them just run away. They don't care about the other 3. Yeah, this one should. Yeah, now, yeah, they are drifting away into the space. By the way, if I tried different combinations of initial conditions, usually this is how it ends. Unfortunately, everything just drifts away from each other, and they stay alone forever. Very sad. Now, if I try another one, and if you look at this system, I like this one because the green keeps spiraling against the red one, and they do this for a long time. I don't know how much, because I usually quit like after a minute, but yeah, they keep doing this, and I like this fact about the system. It is chaotic, but sometimes you get this periodic dance between bodies, and of course, yeah, one always drifts away. And yeah, you can maybe you can try different configurations. This renderer that I did, it accepts, yeah, keyboard, WSAD navigation, and there is R is a reset, and you can just use the mouse to change your camera perspective. Well, yeah, this is another system, and let's try one thing. So if I go to the file, add a tiny velocity, you're gonna see a lot of difference. Now the blue is spiraling against the red, and the green is drifting away all alone. Yeah, all I did was change this number. It isn't a drastic change, but it is a drastic difference enough. Even the spiraling is a difference. So before they were spiraling really close to each other, like in the same trajectory. On this one, there looks like 2 spirals, and they're yeah, that's cool. There's no reason to, you know, there's no reasoning to that. It's just a bit random, but I like it a lot. If I try once more, a different thing, actually I'm gonna add a new body. Let's see what happens. Of course, something completely different. Looks like red is spiraling against the blue and the green is maybe spiraling against the yellow. A negative mass, so it effectively repels all the bodies. It is attracted by the bodies, but it repels them. So look how the blue one is, you know, running away from the yellow. Yeah, so much is possible here. We can, of course, simulate our solar system. So this is a, kind of a small part of the solar system. This is Earth, this is Jupiter, this is Mars. Of course, the simulation is faster than real life, so it is not taking a year for the Earth to go around the sun. One final thing I wanted to note down is that this system step, delta, the smaller the delta, the more precise your system is, but it takes more effort. And all the numeric irregularities that may occur in the step function, so all those divisions, norm, they make the difference if they make the system a bit harder to work with. This is why usually in the step function, if you look at the implementation, usually the step function is not like this. This is one way to approach this problem. So we take a body, look at everyone else, and try to compute the force. Correct way to approach this problem is to form a system of equations, solve the system, and from the system outputs, you're gonna find all the forces to all the bodies. So this is not ideal because every time I iterate, I'm already updating one of the bodies, and so the causality may be broken a little bit. But it's a simple simulation. What matters is that we know how to do it, and it works, and it's cool. Well, if you want to try this yourself, I will leave the links to the GitHub repositories in the video description, so feel free to use those. A small note about the OpenGL application, so the OpenGL gRPC server, is that it is meant to be built in your host device. So the simulator is okay to run whenever as a container or whatnot, but the OpenGL is meant to be running the host device. So you have to build it in your system, not inside a container. The N-body simulator is a container application, so it can run from wherever machine. Now, thank you so much for watching this video. I hope you have learned something new. And if you want to discover more stuff with me, just subscribe and follow me.